Hello grade 12s, this is physical science and my name is Gillian. We are going to tackle that big section, chemical equilibrium. Now, if we look at the big ideas, they're just a few and we can have a look at them individually and get to grips with this massive section. So let's have a look at an overview and see what we already know. So my overview in the middle, you can see here, we've got chemical equilibrium. Now, understanding and definitions. So this part here, understanding and definitions, we know a couple of definitions, but the definition for chemical equilibrium, you need to know off by heart. Those keywords are the ones that are going to give you the marks. So open system, you know about an open system. A reaction that happens in an open system can never be or never reach equilibrium because the reversible reaction can never happen. If our products are escaping, then we can't have, our system can't reach an equilibrium, a chemical equilibrium. It needs to be closed. So what does that mean? Either there's a top on the vessel and so the product can't escape, or it happens within a solution. So there is naturally a closing on that, that vessel because it is within solution and no gas is being made in order to escape. So for chemical equilibrium to happen, first of all, we have to have a reversible reaction. If it's not reversible, it's not going to happen. The reaction will continue to its end, and it will not reverse back. So we have to have a reversible reaction. It has to be within a closed system. So we will have a look at that definition in words in a moment. The other things that we need to know about chemical equilibrium are the factors that affect that equilibrium. We're going to dive into three: concentration, temperature, and pressure. You know about pressure, Boyle's law. You know that if we push a gas closer together so that the volume decreases, so we're talking about gases only, the volume decreases, we're forcing those particles of gas together, the pressure is going to go up, it's going to increase because all those particles have nowhere to go, they're bumping into each other and against the side of the container, and so the pressure increases. So Boyle's law is if you decrease the volume, the pressure is going to increase. So it's an inversely proportional relationship, and pressure applies to gas only. Temperature is an interesting one, and we're going to have a look at temperature in relation to graphs and how we can read it off the graph, and can we pick up the patterns that are happening within the graph. Concentration is the number of moles per volume. So we know this equation, which is concentration equals number of moles over volume. For pressure, we know that the volume is inversely proportional to the pressure and vice versa. Graphs, there are two that we're going to look at in a little bit of detail. So the first one is the concentration versus time graph, and you've seen this in rates, so it's nothing new. So if we've got a product and we're checking out its concentration, it is going to do this, a curved line. So the concentration of the product starts at 0, and as the reaction progresses, it then increases. If we're looking at the concentration of a reactant, we see that the reactant starts really high. There's a lot of reactant in that vessel, and as it reacts, it decreases. The same applies for rate versus time. So the rate of the reaction is going to be shown on the graph, and we've got two reactions we're dealing with here in chemical equilibrium. We're dealing with a forward reaction and a reverse reaction, and so that is why on the graph you will see there will be two lines, a forward reaction and a reverse reaction. And so we're going to have a look at that in detail. Calculations Calculations are usually involving the equilibrium constant. The equilibrium constant is denoted by Kc, and we have to write a very specific expression for the equilibrium constant that is particular for a reaction. It's not a general reaction, a general equation. It has to be very specifically set out for that reaction that you are being asked about or that you have been given. So we're going to have a look at Kc and the expression that we write for a specific reaction. Then we have this interesting man, Le Chatelier, and his principle. And Le Chatelier is talking about what happens when a system has already reached chemical equilibrium and there's a disturbance, a knock on the door, a shake-up. How is that equilibrium system going to respond in order to counteract that disturbance? Let's continue now to our first big idea about how do we write the definition for dynamic equilibrium. So dynamic equilibrium is telling us that this equilibrium is moving all the time. We might look at the vessel and think, this isn't moving, there's no reaction happening here. But actually something is. There is a forward reaction and there is a reverse reaction, and that is why it is called dynamic. It is moving. It is reached when the rate, so we're talking about rate again, and rate is time. It's how fast something is happening. So it is per unit time. The rate of the forward reaction equals the rate of the reverse reaction. This has to be a reversible reaction, as we've spoken about, so you have to put in that word. It is a reversible reaction. It doesn't happen for a reaction that goes to completion and stops. And then it has to be in a closed system. Learn that. It is really important. How do we calculate Kc? This expression, how do we write, how do we calculate it? This is our second idea. Now, the equilibrium constant, there are a couple of conditions that we have to remember about it. It only applies for something which is in the gas form and something which is in the aqueous form. It does not apply for something which is in solid or something that is in the liquid phase. And the reason why is because Kc is revolving around concentration. Concentration at equilibrium. Once the system has reached equilibrium, what is the concentration of our products and our reactants? So with a solid and with a liquid, the concentration is always 1. And with 1 times anything is going to be anything. So we disregard something which is in a solid form or something which is in a liquid form. Now, Kc for a chemical equation that has reached equilibrium will be the same unless the temperature of the system is changed. So Kc only changes with temperature. So it changes with temperature. So if temperature is increased or temperature is decreased, then the Kc value is going to change. Otherwise, nothing will make that Kc value change. It is constant. Right, here we have the symbols that we're going to use for concentration. They're square brackets. Concentration, we know, is the number of moles divided by the volume. For a particular reaction, we are going to express the Kc value as follows. I've given you an example here. It is the formation of ammonia gas. You can see that nitrogen gas is used, so is hydrogen gas as the reactant. It produces ammonia gas. It is a reversible reaction. So ammonia gas then breaks down to form the hydrogen and the nitrogen gas. We can use all three of those substances because they are all in gas form. So what is Kc really? The equilibrium constant is looking at the ratio, the comparison between the concentration of the product and the concentration of the reactant, of the forward reaction. So Kc here is the symbol, and the concentration of the product of the forward reaction is NH3. Now you will see there is an exponent 2 over there, and that correlates with the coefficient of the ammonia gas. So this reaction, before we can write the Kc, this reaction has to be balanced so that we can maintain the conservation of atoms. So it's a balanced reaction equation, and the 2, that is the coefficient of ammonia, is then placed as an exponent. So we square the concentration of ammonia gas. We divide that by the concentration of nitrogen gas and the concentration of hydrogen gas. It's times together. And look here, we cube the concentration of hydrogen gas. Why? Because it has got a coefficient of 3. So when you are writing this, you need to be extremely particular about the expression that you're writing. It has to be specific for the balanced equation of the reaction that has been given to you. Now, if Kc is greater than 1, it means that the concentration of the product of the forward reaction is high. And so we can figure out where this equilibrium is sitting. We can figure out at equilibrium there is a large concentration of product formed. If Kc has a value which is smaller than 1, it's less than 1, then we know that this concentration of product for the forward reaction is low. We get a low value of Kc. That means that the value of the concentration of the product is low. So the Kc value is not just a number. It tells us a lot about where the equilibrium sits. Right, grade 12s, it's time for a brain break. We'll see you later. Welcome back, grade 12s. We have been busy looking at Kc, the equilibrium constant, and now we need to check out how are we going to use this in a problem, in a calculation. So you might have heard of this. It's the Rice table, which stands for ratio. R is ratio, I is initial mole concentration, or number of moles. C is the change in the moles, and E is the equilibrium, what's happening at equilibrium. So we use this as a tracking for ourselves. It's to plan out how the number of moles of a substance changes initially, through the reaction, and then finally at equilibrium what is happening. So if you look at my screen here, you'll see right at the bottom, it says here concentration at equilibrium. Now, we've already looked at that equation. Concentration is equal to number of moles over volume, and concentration at equilibrium is where we get our Kc value from. So that is where Kc fits in. We're looking at the concentration of the substances when they have reached equilibrium. I have given you in this table a phantom equation. You can see there it's A, B, and C. My reactants are A gas and B gas, and my product is C gas. I have a double arrow telling me that it is a reversible reaction, and it is balanced. You can see I have 2 in front of the A. So that balanced reaction is going to give me the ratio at which the reactants react to form the product, and the other way around, the way that the product then reacts to form the reactant for the reversible reaction. Initially, at the very start of the reaction, I will have no product. There we go, it is 0. There's no product, there are no moles formed. So, I will only have moles of A and B, my reactants, and I'm giving you those. So I'm saying initially at the start of the reaction, I have 12 moles of A, 15 moles of A, and I've got 12 moles of B. Now, let me tell you, this I'm telling you, I'm giving it to you, that in this reaction, there is a change in the product, and the change is 4 mole. So that means that 4 mole of C is formed during the reaction, and so at equilibrium I will have 4 mole of C. So now I'm going to work back. How does that then impact the reactants and how they are being used up? So the change in mole, I need to use the ratio. So if 4 moles of C are formed, the ratio is 1 to 1, so 4 mole of B will be used up. We put a minus there because it's used up. For the ratio of A to C, you can see that's going to be 2 is to 1. So if 4 mole of C is formed, then 8 mole of A is going to be used up. So you can see there that we're getting further and further into our calculation. So at equilibrium, what will the number of mole be for each of these substances? So we're going to subtract, because the change in mole is what is used up by A, or how A is being used up. So 15 minus 8 is going to be 7, so there'll be 7 mole. 12 minus 4 is 8, and so they're going to be 8 mole of B, and of course we have then 4 mole of C that is formed. Now, the concentration at equilibrium, according to this equation, is number of mole divided by the volume. So if we say that the volume is a decimeter, then we can divide each one of these by the number 1 decimeter, and so we'll get an answer of 7 decimeters, 7 mole per decimeter. I'm just going to put that in there, that's the concentration. This one would be 8, so 8 mole per decimeter cubed, and then this one would be 4 mole per decimeter cubed. Okay, so this is how we use the Rice table. It is very helpful in formulating what is happening with the number of moles of substances, the reactants and the products, and we can then figure out the number of moles at equilibrium, and from there we can calculate the concentration. And once we know the concentration, which is mole per decimeter cubed, we can then calculate Kc. Let's move on to our third big idea, which is Le Chatelier. Now, Le Chatelier's principle, you need to know off by heart as well. So when the equilibrium in a closed system is disturbed, that big word, disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose the disturbance. You need to know that off by heart. So how do we apply Le Chatelier? There are 2 ways we can be asked Le Chatelier. The one is we are told what the disturbance is, and then we have to say in words how we're going to answer these questions. In words, this is what we have to do. We need to identify the distress or the stress. We need to write it in words. We need to state how the system is going to respond to that distress. We need to state which reaction is favored, and then we have to say what effect is the new equilibrium going to have. The second way we can be asked Le Chatelier is by looking at the graph. So there's 2 graphs. the rate versus time graph and the concentration versus time graph, and we can see a disturbance in those graphs, and we'll need to be able to interpret them and then write in words what is happening in that particular reaction. So let's have a look at this concentration versus time. It is a well-known graph. You can have a look at it. This is for the same reaction of making ammonia. It is reversible. Please take note of this change in enthalpy. It is important in temperature, but you can see that the concentration is decreasing of the reactants there, nitrogen and hydrogen, and it is increasing for the ammonia until equilibrium is reached. And when that is reached, when the rate of the forward reaction is the same as the rate of the reverse reaction, the lines are parallel to the x-axis. So all those lines are straight lines, they're horizontal lines, and that is when we know that equilibrium has been reached. So if we start adding a disturbance, so we mess around with the concentration, we can either increase the concentration or we can decrease the concentration. What is it going to look like on this graph? So if you look at the concentration versus time graph, you can see that equilibrium has already been reached. You can see that those lines are horizontal and parallel to the x-axis. Now what happens is one of those components, you can see the hydrogen there is in the yellow, suddenly peaks. Look at that. It goes straight up. It is a vertical line. Something has happened to disturb the equilibrium. And for this, it's going to be this particular line that you see is telling you that the concentration of the hydrogen has changed and it has been increased. So when we write out Le Chatelier, his principle, we write out what's going to happen. We're going to follow those four things. So what is the stress or the distress? Well, there has been an increase in hydrogen concentration. You need to write it. An increase in hydrogen concentration. What is the response? So what is going to happen to the system to try and alleviate that stress? Well, the system's going to try and decrease now that increase in hydrogen. And so what's it going to do? It is going to try and take away that increased concentration. And so the system will react to decrease the hydrogen concentration. There we go. We're going to write it in words. Which reaction is favored then? Well, it has to be the forward reaction, because the forward reaction is the one that's going to take away the hydrogen it's been used up to form something new. So the forward reaction is favored. What is the effect then? Well, there's going to be an increase in the concentration of ammonia gas and a decrease in the concentration of nitrogen gas. I think we have a few more minutes to have a look at this. When we look at the rate versus time graph, you can see over here, that is where equilibrium has been reached prior to the disturbance. Now there's a disturbance. There are two lines here, one telling you that we have a forward reaction and one telling you that we have a reverse reaction. So you can see here there's a vertical line. It is telling you the disturbance is in the forward reaction. Somehow the rate of the forward reaction has increased dramatically. And so you can read from that that there has been a disturbance in the concentration of either hydrogen or nitrogen in this case, we don't know which one, and the equilibrium has shifted to alleviate that distress and has favored the forward reaction. Once again, you see here the lines are parallel, and so equilibrium, a new equilibrium has been reached. I want to speak quickly about temperature because temperature is quite interesting. Temperature is going to affect both the forward and the reverse reaction. However, there is going to be one reaction which is favored because of the change in enthalpy. So when we try and write about Le Chatelier and the disturbance of temperature, we need to look at the reaction that's given to us and the change in enthalpy. We know that if delta H is a positive value, then the forward reaction is endothermic. If delta H is a negative value, then the forward reaction is an exothermic reaction. So exothermic is releasing energy, endothermic is taking in energy. So if we have an increase in temperature, the reaction which is going to remove that increase in temperature is going to be favored. So for this reaction, the forward reaction is exothermic. Let's say we increase the temperature, it's increased. The reaction that's going to use up the heat is going to be favored, and so that is going to be the reverse reaction. The reverse reaction is endothermic. That's going to absorb the heat, the increase in temperature, the energy, and so the reverse reaction is going to be favored. In terms of Le Chatelier, this is how we write it. Stress, what is the stress? There's an increase in the temperature. What is the response? The system is going to respond to decrease the temperature increase. So which one is favored? The endothermic reaction is going to be favored, and in this case it is the reverse reaction. What is the effect? Well, the ammonia gas concentration is going to decrease, but the product concentration is going to increase. So the first question is quite a big question, and it covers quite a lot of information that we should know. It says here, it sets the scene. The dissociation of iodine molecules to iodine atoms is a reversible reaction taking place in a sealed container at 727 degrees Celsius. So from that reading, we know then that we have a constant temperature at 727 degrees Celsius. We know that it is a dissociation reaction, that we're dealing with iodine molecules, and that we also have iodine atoms. They give us the balanced equation. They tell us that it's balanced, and we can see here that iodine, the diatomic iodine gas, will form iodine atoms, and that is also in the gaseous phase. It is reversible, so the reversible reaction is possible. The Kc for the reaction at this particular temperature is 3,76 times 10 to the minus 3. Kc does not have any units. It's got no units, and the reason why it has no units is because it's a comparison. It is a ratio between the concentration of reactants and the concentration of products, and that is once equilibrium has been established. Kc can only be changed when there is a change in temperature. Nothing else can change Kc. What are they going to ask us? The very first thing they ask us is, write down the meaning of the term reversible reaction. Now, this is nothing that you have, it's not a definition that you've learned, but they're asking about an understanding. So what is a reversible reaction? Well, a reversible reaction is one in which the reactants form products, and then the products can then form the reactants again. So you could say that. You could say that both the forward reaction and the reverse reaction is possible. So those are two options for you that you could use. The next question is quite detailed. They're now asking you to use your understanding and your knowledge and put them together. At equilibrium, the pressure of the system is increased by decreasing the volume. This works for a gas only. Only a gas responds to a change in volume. The temperature remains constant. So they're now going to give us scenarios and ask us how are these things going to be affected. So how will each of the following be affected? The first one is the value of the equilibrium constant. Now, we already know this. The equilibrium constant, Kc, is only affected by temperature. That's the only time it can change. Is this temperature? No, it's not temperature. It is a constant temperature. It is the pressure which is changing. So, how will it be affected? How will the Kc value be affected? It will not be. It remains the same. The second question, how will the number of molecules of diatomic iodine be affected? So, because we are changing the volume, so it was a big volume of container, we're now changing it to a little volume, it's a smaller volume. With Boyle's law, there is an inversely proportional relationship. A decrease in volume increases the pressure. In an equilibrium situation, the equilibrium will always shift to try and alleviate the number of moles, because when we're decreasing the volume and therefore increasing the pressure, the thing that is causing the pressure is the number of moles, the number of particles that is in that space. So the equilibrium will shift to try and reduce the number of molecules or number of moles that is in that particular space. Obviously, that would make sense, right? So when we've got to look at our balanced equation over here, which is I2, reacts to form 2I. So you can see that there are 2 moles of the atoms of iodine there and 1 mole of iodine, diatomic iodine. So which way is it going to shift? Well, obviously the equilibrium is going to shift to alleviate the number of moles, so it's going to shift in this way. And so what is going to happen with these, the number of iodine molecules? Well, it's going to increase. So the answer for this is increases. So the number of iodine molecules increases. That's quite a lot of thought work, right? Just for one answer. But you need to think through that so that you can get the correct answer, even if it is worth only 2 marks. Now, the next question is explain what we have just done. Explain your answer, which is the increase in iodine molecules. Explain it and refer in your explanation to Le Chatelier's principle. In our Big Ideas lesson, we spoke about this. How do we answer in terms of Le Chatelier? There are 4 things. Distress. We have to say, what is the distress? We have to say, how is the system going to respond to that distress? Which reaction is favored? And what effect will the new equilibrium have when it is reached? So let's put what we have just spoken about into words. So we've said that with an increase in pressure, the system is going to try and alleviate the number of moles. And so we're moving from 2 moles to 1 mole, and so the equilibrium is going to shift in that direction. What is the stress? So the distress or the stress here, I've just put a reminder up for us. So the distress is going to be that there is pressure that is increased because we have reduced the volume. So the stress is the pressure is increasing. What is the response? Well, obviously the equilibrium is going to shift so that it can decrease that pressure. And how is it going to do that? It's going to do that by reducing the number of moles of gas. So we write there, the system reacts to decrease the pressure by forming less moles of gas. There we go, it's forming less moles of gas. You can write decrease if you want to too. So which reaction is favored? So we're on to this one here. There, which one is favored? It is going to be the reverse reaction. The reverse reaction is favored. And once the new equilibrium is reached, what are we going to see? What is the effect of that? Well, the I2 concentration is going to increase. And what about I? Well, that concentration is going to decrease. And we write it like that. Our next question is looking at the Kc value. So I have written this equation up here again, just to keep us remembering what we're dealing with. 1.4 says that at this temperature, 227 degrees Celsius, the Kc value for the reaction we're dealing with is this value here, 5,6 times 10 to the minus 12. Is the forward reaction endothermic or exothermic? And you need to explain your answer. Now, there is a little bit of information that they gave us right at the very beginning of this question, and it was this here. Have a look at that. The Kc for the reaction at 727 degrees Celsius is 3,76 times 10 to the minus 3. So this is the initial temperature of the reaction. They're now telling us that something has happened. And what has happened is a decrease in temperature. So our temperature has decreased. How do I know that? Because we started off with 727 degrees Celsius, and the temperature is now at 227 degrees Celsius. It has decreased. What about Kc? Well, our Kc expression for this particular reaction is going to be the concentration of I squared. Remember, that comes from the number of moles, the coefficient in front, divided by the concentration of I2. So these are the products divided by the concentration of the reactants. So that is the specific Kc expression for this reaction. What is happening to the Kc value? So the first Kc value is that one there. So the Kc value is 3,76 times 10 to the minus 3. It has not got a unit because we're talking about a ratio or a comparison. It is decreasing. Have a look at that. The Kc value has dropped to 5,6 times 10 to the minus 12. So the Kc value has also decreased. It has also decreased. So if our Kc value is decreasing with this disruption, it means that the amount, the concentration of I must have decreased as well. So our concentration of product has decreased to give us a lower Kc value. So Kc, remember we spoke about this in the first video, that Kc, if it is smaller than 0, then we're talking about our concentration of products being lower. So with a decrease in temperature, the concentration of I is less. I is less. So if we drop the temperature, what is happening? That reaction is being favored. The reverse reaction is being favored. A drop in temperature means that the reaction the equilibrium has to change to create more energy, more heat. So that is, the exothermic reaction is favored. And so this reaction, the reverse reaction, is going to be exothermic. But that is not the question. The question says, is the forward reaction endothermic or exothermic? So the forward reaction has to be an endothermic reaction. It is time for a break, grade 12s. I will see you just now. Hello, grade 12s. We are back from our break, and we have been busy working out which reaction is endothermic or exothermic. The Ford reaction, what is that? And it was round about the equilibrium reaction of iodine molecules forming iodine atoms. Now, in this particular question, there was a lot of working out in our minds. We had to figure out what was going on. The answer is one word. It's either endothermic or exothermic. But they ask us to fully explain our answer. So here we go. How are we going to write this in words to get all our marks and to make sense to the examiner? So our Kc value decreases. We found that. It decreases with a decrease in temperature. So the Kc value, remember we had to use the initial Kc value that was hidden right on top of the page. So the Kc value decreases with a decrease in temperature. So what you observe, that's just from observation. The reverse reaction is going to be favored with this decrease in temperature. The concentration then of the reactants is going to increase, you could say that, or you could say the concentration of the products is going to decrease. Remember that our reaction was moving from iodine atoms to iodine molecules. What does that mean? It means that the yield, that means how much is made, our products, the yield is decreasing. So what is happening here? The decrease in temperature favors the exothermic reaction. So all these words are explaining step by step our thought processes in unpacking this question. And then that gives us the answer, which is endothermic. It is good to practice writing these answers down so that it is easier for you in an assessment situation. It can just roll off your pen. The next question I want us to tackle is the one that uses the Rice table. Our putting down in a structured way our calculations of a reaction in the beginning, the initial number of moles that are available, the middle, what's happening to the change in the moles as equilibrium is reached, and then at the end, when equilibrium is reached, what is the moles of each component of the reaction. And from there, we can then calculate the concentration and obviously Kc. So this is a really tricky question. It requires a lot of thought. You need to set out your work very clearly and explain exactly what you're doing. So in other words, write down your maths. It's like doing a maths exam, writing down your steps of calculation very carefully. So the question says, a certain mass of iodine molecules, I2, is sealed in a 12.3 decimeter cubed flask. That is telling me my volume. Okay, it's telling me what the volume is. At a temperature of 727 degrees Celsius, and at that temperature, they give us the constant. The equilibrium constant, 3,76 times 10 to the minus 3. When equilibrium is reached, the concentration of the iodine atoms is found to be that amount. So 4,79 times 10 to the minus 3 mole per decimeter cubed. So that is the concentration of the iodine atoms. Okay, concentration of the iodine atoms. Calculate the initial mass of the iodine molecules in the flask. Okay, so have a look at here. Molecules, the word is telling us that they are looking for I2, the diatomic molecules. So where do we start? We're going to take all this information that we've got and we're going to put it onto our Rice table. So here we've got our Rice table. Rice stands for ratio, R. The ratio, what is the ratio in the that has been formed in the equilibrium reaction? So this is the reaction. I've placed it here for you. They gave it to us at the beginning of the question. We've got the iodine molecule, diatomic molecule, reacting to form iodine atoms there. They're both gas. It is balanced. Our ratio is going to be 1:2. Okay. What's the next thing? I stands for initial moles. So the initial number of moles. We have not been told anything. We don't know what the iodine molecules are, what the initial number of moles is at the beginning of this reaction. Nothing. We do know, though, that when the reaction starts, that the number of moles of product is going to be 0. So we do have that. Now, change in mole. We don't know anything. They haven't told us anything about that. So the C in the right stands for change in, so that's why it's delta, change in the number of moles as the reaction reaches equilibrium. And then at equilibrium, what is the number of moles? Well, we don't know that either. We do know, however, if I go back to the slide, they have told us that the don't tell us the number of moles, they tell us the concentration of the iodine atoms is 4.79 times 10 to the minus 3 moles per decimeter cubed. So that is concentration. So I can't fill anything into these two rows for now, but what I can do is I can fill in the concentration of the iodine atoms at equilibrium. What else do they tell us? This is quite a little bit of information. They do tell us the Kc value. That is one thing they do tell us. And they tell us at this equilibrium that the Kc value is 3.76 times 10 to the minus 3. We have the concentration for the product. So there is our formula. Remember, we've got an expression for every single equation reaction that we come across. It's very specific. The Kc expression is very specific for every single reaction. So there it is there. You need to write that. That's the one you need to write. And you can see that the product is squared. Why? Because there is 2 coefficient. So we square this value, this concentration that has been given to us. We calculate it all out, and we can then find the concentration of the diatomic iodine molecule at equilibrium. So we've worked all that out, and we get an answer of 6.102 times 10 to the minus 3. It will be moles per decimeter cubed. Okay, so we're one step further. We have discovered what the concentration is of the diatomic iodine molecule at equilibrium. From our equation of concentration, we know that C is equal to number of moles over volume. We are told what the volume is. They told us it's in a flask, which is 12.3 decimeters cubed. So if we rearrange our formula, we can work out the number of moles. We say number of moles is the concentration, which we've just figured out here. So we figured that one out. We were given that one. We can work out the concentration. From the concentration, we can work out the number of moles, timesing it by the volume. So this is the volume here, and we times both concentrations by the same volume because they're in the same flask, and we end up with an answer of this. So we've got 0.0589 moles at equilibrium for the atoms, and we have got 0.0751 moles for the molecule at equilibrium. What is the change in number of mole, though? Because that is really what we want to find out. So for our product, we know that this is going to be the same value. How many moles of iodine molecules are used up? Well, we need to use our ratio. So our ratio, as we've said before, is 1 to 2. And so if we take the number of moles that have been formed through equilibrium, we divide it by 2, we can then get this answer here using the ratio. So we now have figured out the number of moles of molecule, iodine molecule, that is used up in this reaction. And that helps us because now we can work on how to find and calculate the mass, because that was the question. What is the mass of iodine molecules that is used up? So our initial number of moles is this. Once we've gone through our calculations, it's 0.1045. Now we can work with our standard equation or formula. We get this from our periodic table, periodic table, your data sheet, which is mass is equal to molar mass times number of moles. The molar mass from the periodic table is 254 grams per mole. We times it by the number of moles that we have discovered or calculated, and we end up with this answer. So the mass of iodine molecules involved in this equilibrium reaction is 26,543 grams. That was a massive question. So grade 12s, I hope that helps you with formulating your thoughts and thinking through these tricky kinds of questions. The rest of these answers you will find on the Yellow Ed platform. Please go and try them out and then check your answers from the answer sheet. Right, go well.